Welcome back. This week we'll be talking about forecasting tools and methods. We'll cover different types of diagnostics and forecasting with transformation, decomposition, evaluation for our forecasting prediction model, and also time series cross-validation. But first, I'd like us to review two important concepts of white noise and random walk and why it is important for prediction or for forecasting. First, why is the white noise so important? Recall from our previous chapters, we define white noise with a mean of 0 and with the variables that are independently and identically distributed. So white noise is important for two main reasons. Predictability. So if our time series has white noise, then by definition it is random and we cannot reasonably predict our model because it's random. The second important reason is for model diagnostics. In fact, we do want to have a white noise in our evaluation in a forecast error model. Because if our forecast errors do not look like white noise, we need to look for improving our model, our predictive model. Here's an example of white noise model that we created using random normal distribution. So when you explore your model visually, look for the following questions. Does your time series have a non-zero mean? Does the variance change over time? And do value correlate with like values? We can check the mean and the variance, and we can just look at summary to see if our mean is 0, close to 0. Secondly, we can create autocorrelation plot, which you're now very familiar with. We can create autocorrelation plot, which you're all by now familiar with, and we expect each autocorrelation to be very close to 0. It may not be exactly close to 0 because we're still using some random variation, but we do expect it to be within our significant interval. All right, let's move to random walk. First of all, random walk is not just a list of random numbers, because in our design, we always have a next value dependent on the previous value in the sequence. So dependence from one step to the next. And unlike white noise, our random walk has non-zero mean and non-constant standard deviation. Random walks typically display long periods of trends that can go up and down, and also sudden and unpredictable changes in directions. Let's look at this random walk, for example. It looked like a trend, right? There's a trend down and then trend goes up. To create random walk, to simulate random walk, we can use a function that would take a number of periods, initial value, and a drift. So we'll start function with random normal distribution to generate random normal variables, and then we use cum sum that will get us a random walk. So this is our function. We're adding number of periods from 1 to 50. Our random walk will have initial value, let's say 10, 0 drift, and we can build example. Notice that every time you run your plot, you may have a different representation of random walk because it's based on random numbers. But in general, it does display some random variation and some additional trends that may go up and down. So these are typical characteristics. So if we think about forecasting using a random walk, our forecasting model will be equal to the last observation because the future movements are unpredictable. Our model is built using the following formula. So our current value is always equal to previous value with some noise. Right? This is a model. We start with a random number, then we randomly select another number and just add it to the observation from previous steps. And we just repeat this step, and that's why we have our cum sum, a cumulative sum, to build our random walk. Another type of random walk could be with drift, where instead of 0, we add some constant value. Drift is often denoted with mu, and it's and the drift means just a gradually changing, right? For instance, stocks may fluctuate constantly, but they may also exhibit some positive drift. So our formula include this mu, this constant, that will be exhibiting this gradual increase in addition to previous value and noise. So if you look at random walk with drift, this constant value does display a positive drift that look like a trend. So in this case, we use 0.5 for mu value. If you look at autocorrelation plot, we'll find a very strong autocorrelation with previous observation. It shows very strong correlation and dependence on the previous step. Let's remind ourselves what is stationary time series is compared to non-stationary time series. So in stationary time series is when our values do not depend on time, so they're not function of time. But if you look at observation in a random walk, they are very dependent on time. So the random walk is not stationary. So we can say that all random walk processes are non-stationary. Just keep in mind that not all non-stationary time series are random walks. All right. So we have several tools that will let us check if our time series is random walk. One is differencing, and the second one is ADF test. Differencing is a task of computing differences between consecutive observations. So truly we can make our random walk stationary when we take the difference. We replace each observation as a difference between the current and the previous one. So we can use it by applying function difference to our time series values and plotting. And this is our random walk with drift, but after differencing. We don't really see any trend in this plot as compared to random walk with drift before differencing. And if you look at our autocorrelation plot, we don't really see significant relationship between our lag observation except a couple of perhaps outliers, because by design we based it on random numbers, right? So those kind of random outliers. And the second tool for us to test whether we're dealing with random walk, because remember, with random walk we cannot really use it for predicting or forecasting. So we can use the augmented Dickey-Fuller test, ADF test. And this test is a common statistical tool to evaluate whether our time series is stationary or not. Remember, the random walk is a non-stationary time series. So our null hypothesis is the time series is non-stationary. So if our p is greater than statistically significant level, we fail to reject our null hypothesis that time series is non-stationary. So we can apply our ADF test, and based on the results, our p-value is 0.6. So we fail to reject null hypothesis, which proves that our time series is non-stationary. In this case, it's a random walk. So key points to take away is that random walk cannot be reasonably predicted. And the best prediction that we can apply is perhaps just using the observation at the previous time step, right? t-1 is what will happen in the next time step. And this type of prediction is often called the naive forecast. We'll talk about it in our next lecture. This is also called persistent model. So the second key takeaway is that white noise, if our time series is white noise, we cannot use it for prediction because it's random. All right? So these are two main points that I wanted us to discuss before diving into the forecasting methods and tools. White noise and random walk and their importance for prediction. All right? See you soon for our next forecasting methods and tools.